This lesson is about the line of fit and residuals. We're specifically going to look at linear lines of fit, which means straight lines. If we have a scatter plot, we have a bunch of different coordinates, points, graphed with the y and the x-axis. In this case, we're comparing the amount of money that someone spends on entertainment versus the number of hours that they work. We are asked to draw the line of fit for this scatter plot and then estimate the equation for that line. Well, a line of fit is a line that goes through pretty much the center of those dots and follows the pattern. So we're going to try to draw a line through the center of those dots that follows the pattern going upwards. This is called the line of fit. All we have to do is get as close as we can. To write an equation for this line, we're going to estimate two different points and use the equation y equals mx plus b, where m is the slope of the line and b is the y-intercept. Looking at our line, we can estimate 2 points, about where they are. We don't have to be exact, but we just want to get as close as we can. Remember, these 2 points have to be on the line. In order to find the slope, we're going to see the rise over run for the point 11, 17 and 18, 24. We can simply subtract the y-coordinates and the x-coordinates. Remember, x always comes first in the parentheses and y always comes second. And then we can simplify that and find our slope. In this case, the slope is 1. So far, we have y equals 1x plus b. Now we have to find the y-intercept. In order to find the y-intercept, we want to ignore one point and just focus on the other. In this case, x equals 11 and y equals 17. And we're going to plug those values into our formula so far, where the y-coordinate is 17 and the x-coordinate is 11. Then we solve this equation for b by multiplying 1 times 11 and then by subtracting 11 on both sides to cancel it out and find out that b equals 6. Now that we know b is 6, we can plug it into the last remaining section of our equation and we get y equals 1x plus 6. 6 is our y-intercept and 1 is our slope. Once we have a line of fit, we can calculate residuals, comparing how close each point is to our line of best fit. In this example, we have a table showing the amount of time that someone has spent studying versus their midterm score. This has been graphed on a graph with x and y axis, where x is the time spent studying and y is the midterm score. And we've already found an equation. Y equals 3.8x plus 14.76. We're going to find the residuals by comparing the observed score and the predicted score. The predicted score will come from the equation that we predict, and the observed score will come from the table where we have the actual values. Let's find the observed scores first. For somebody who spent 12.1 hours studying, their observed midterm score was 70.00. And for someone who spent 14.9 hours studying, their score was 65.00. Remember, observed comes from the table. In order to find the predicted score, we're going to have to plug those values into our equation. If we go up to our line of best fit equation and we plug in 12.1, the answer we get is going to be the predicted midterm score, 60.74. Now we're going to go up to our equation and plug in 14.9. The answer we get, 71.37, is the predicted midterm score for someone who studied 14.9 hours. In order to calculate the residual, we're going to subtract these two numbers to see the difference. So the observed score subtract the predicted score equals the residual. First, we would do 70 subtract 60.74, which is 9.26. For the second residual, we would do 65 subtract 71.37, which is negative 6.37. So the residual is the score from the table, subtract the score you get when you plug it into the equation. If we graph these residual numbers, we get what's called a residual plot. Residual plots show how close our line of fit is to describing those patterns that we found in the points. If we compare a residual plot with the line of fit, you'll see a distinct pattern. It's almost as if we take that line of best fit and turn it until it lines up with the x-axis, and all of the points follow, staying the same distance from the line of fit as they were before. If all of the dots line up perfectly on our line of best fit, we get a residual where all of those dots line up perfectly on the x-axis. This is called a perfect fit. This means that all of the dots were on our line, so our line fits those dots perfectly. If all of the dots are equally and randomly spaced above and below that line, it's still a good fit. We have the line going through the middle of the dots and following the correct direction. However, if we can see a distinct pattern where the dots are not just randomly spaced above and below that line in the residual plot, that means it is not a good fit. If you can see our line of fit on the right, those dots obviously curve upwards and downwards, and a straight line going through the center doesn't really fit the direction the dots are going. If we have a nonlinear graph, which means it's curving, then our line of best fit should also curve to fit those dots. This one is actually what a quadratic equation would look like, a quadratic function. It's curving, it's not a straight line, it's not linear. Just check to make sure. If all of the points on the residual plot are evenly spaced above and below and randomly spaced above and below the x-axis, then it's a good fit. But if you can see a distinct pattern above and below that residual, especially a curved pattern, then that's not a good fit for the line.